So next we're going to talk about basically the beginning of chapter 4, where different models of the atom, as we learned about the world around us, learned about atoms and nuclei and that sort of thing. So starting off, we had John Dalton. So he had his atomic theory. So this is early 1800s. But he had these 5 things that are composed of his atomic theory. So number 1, he believed that an element was composed of tiny, indivisible, indestructible particles called atoms. And we now know that number 1 is actually not entirely true, which we are going to get into in this video. Number 2, all atoms of an element are identical and have the same properties. So actually, this one also is not technically true. Not all atoms of a single element are totally identical. So this one's not true today. We know better. 3, 4, and 5 are true. So number 3, atoms of different elements combine to form compounds. So that's an example of like hydrogen and oxygen. We could make H2O. Number 4, compounds contain atoms in small whole number ratios. That's also correct. We're never going to have half of an atom, for example. And then number 5, atoms can combine in more than one ratio to form different compounds. So hydrogen and oxygen are not always H2O. We can also have H2O2, that's hydrogen peroxide. We could also have OH, where it's also got a negative charge associated with it, and we call that hydroxide. But they can combine in more than one ratio, and that's kind of what we're seeing in this part of his diagram. So this is from his work. We've got, these are the different elements that he was working with, and then he's noticing that they can combine in different ratios, and they're always small whole number ratios, so we never have like half of a circle in this drawing. But again, number 1 and number 2 are technically not correct, and we're going to get into that. So next we have Thomson's model of the atom. So just to clarify, Dalton's was not the model of an atom, it was just the theory about atoms. But then actually trying to get into what does an atom really look like, Thomson's model, they discovered by the time Thomson came around and at the end of the 1800s that there must be subatomic particles out there. And they discovered that we must have these two. So some negatively charged particles, which they called electrons. And this is the notation that we'll use. And then positively charged particles, which we call protons. And this is the notation we use for that. So an electron has a relative charge of +1, and a proton relative charge of electron is minus, proton is plus, but we say relative charge because we have a unit for charge called the coulomb, which is what we use to actually measure electrical charge. But electron and proton have the same, it's just electron is negative and then proton is positive. So it's important to remember that electrons are negative, protons are positive, and they have the same magnitude charge, so the same number of coulombs associated with them. So continuing on his model of the atom, with this knowledge of positive and negative particles, Thomson proposed a model that looks kind of like this, and we call this the plum pudding model, because it's kind of like if you had a bowl of pudding and then a bunch of positive, the pudding itself is all positiveness, if you will, and then the electrons are kind of like, sometimes there's also the raisin plum pudding or raisin pudding, but it's like if you had a bunch of raisins in a bunch of pudding. I guess that's where it comes from, but the electrons are actual particles, and then they're inside this like soup or sea of positive charge. That's the plum pudding of the model. That's what they originally thought in 1903. So the electrons are evenly distributed throughout a homogeneous sphere of positive charge. And at that point, he could only calculate the mass to charge ratio of a proton and electron. So he didn't know the mass, he didn't know the charge, he just knew the ratio of the two. So to actually get the charge, we have Millikan. So in his famous oil drop experiment, and this is kind of a schematic of what he did, but he was able to determine the exact charge of an electron in 1911. So what we have happening in this diagram, we've got like an oil sprayer. So there's oil in here, and then this will turn it into droplets as he sprays into this chamber. And so we'll have lots of little oil droplets inside this box. And as they float downwards, they'll eventually pass through this little hole. And then in between these two plates, so we've got two electrical plates here, we're setting up a charge. So there's a uniform electric field in between these two plates. And this little part of it, this is showing that this bottom plate is connected to ground. It's kind of like an electrical wire literally being stuck into the ground. And when an oil droplet, initially what happens when an oil droplet comes out of the sprayer, it actually picks up a little bit of charge, kind of like you picking up static electricity when it's really, really dry and cooler in the winter walking across your carpet. The oil droplets will also have a little bit of static electricity, so they'll have a charge just by virtue of being sprayed out of that, being like aerosolized, or I'm not saying the word right, but they'll have a little bit of charge, and when they fall through that little hole, once they enter that electric field, they're no longer going to be falling at a uniform rate. So everyone's probably familiar, if you drop a ball, it'll fall the same way every single time. When these little droplets would fall through this little region of the electric field, how fast they fall depends on how much charge they had. And this is getting into more physics, and I don't want you to worry about the details too much, but what Millikan had to do is look through a microscope, and he's literally watching these little droplets fall. Sometimes they fall faster, sometimes they fall slower. And putting it all together, he was able to determine the exact charge of an electron. And this capital C, this is that coulombs I was talking about. So electric charge is actually measured in coulombs, and then we can, quantify the charge on an electron. And here you see we've got it up to 5 sig figs. But for this class, we just need to worry about the fact that an electron is essentially -1. It's not -1 coulomb, it's just -1. And then a proton is +1. So if a electron is -1 and it's -1.5924 times 10 to the -19th coulombs, then a proton must be positive 1.5924 times 10 to the -19th coulombs. So next came Rutherford's model of the atom. Now Rutherford and his graduate students, what they did is they fired alpha particles at thin gold foil. So this is called Rutherford's gold foil experiment because he was basically using gold foil. And you might be asking, what are alpha particles? Well, essentially, alpha particles are helium nuclei. So helium, element number 2, symbol is He. Helium is essentially 2 protons and 2 neutrons in the nucleus, and then there are 2 electrons outside the nucleus. And this is kind of the end story, is, this is the structure of the atom we're going to discover, but I'm saying if you take away those 2 electrons and you're just left with the nucleus, that's what an alpha particle is. That's an alpha particle. Now, with Rutherford's model, this experiment, if the plum pudding model was correct, then the alpha particles should go straight through the gold foil. It should go straight through the atoms. And that's what he was testing. But what was very, very interesting was that some of the alpha particles actually bounced backwards. And this was the amazing result of his experiment. So just kind of schematically, what we saw, or what he saw. So some of the alpha particles would go straight through, but then some of them actually bounce back. Some of them would bounce and be deflected a little bit, so that's what we're seeing right here. So many of them, went straight through, but many of them were deflected, and some of them bounced backwards as well. So from this result, he was able to conclude that the center of an atom, which we're calling the nucleus, must have been extremely dense, like firing a bullet at a piece of paper and it bounces right back. That was his analogy. But he was also able to figure out the diameter of an atom. So 1 times 10 to the -8 centimeters, and that's rough because atoms do have different diameters. There's such things as small atoms and large atoms. And then the nucleus is even tinier, so about 5 orders of magnitude smaller, 10 to the -13 centimeters. So just kind of reviewing scientific notation, I said 5 orders of magnitude smaller because 13 minus 8 is 5. So to put it in perspective, if an atom were the size of the Superdome, the nucleus would be the size of the marble. So atoms truly are mostly empty space. If our atom is this big, I wouldn't even be able to draw it, but the nucleus would be some teeny tiny, ridiculously small dot. This is the atom, and then that's the nucleus. So Rutherford predicted that it must contain neutral particles in addition to protons. So these neutral particles, we're going to call neutrons, and then this is how we write the notation for that. But the neutron, what you need to know, it's about the same size as a proton, but it has no charge. And then these neutrons with the protons are in the middle of the atom. They're in the nucleus. So that's why we have in this table, protons and neutrons are together inside the nucleus, and neutrons do serve a very, very important role in terms of nuclear chemistry and nuclear physics. But the protons and neutrons are there together, while the electrons are on the outside. And here are our symbols, so we already saw these. So the electron is negatively charged, so that's why it has a little negative sign. And then the proton is positively charged, so that's why we have a little positive sign for proton. And then neutrons, being neutral, they have no charge. There's a little 0 for that one. So relative charge, we said neutrons are neutral, that's why they have no charge. And then we said electrons are negative and protons are positive. So compared to each other, we'll just say electrons are just 1 minus and protons are 1 plus. And then mass, this is an interesting one. So protons and neutrons, they're not exactly the same mass, but they're pretty much the same for our purposes, which is fine. There is a very, very, very slight difference, but we're not going to worry about that. However, electrons are incredibly tiny. Electrons are ridiculously tiny compared to the proton and the neutron. And this has implications when we're talking about the mass of atoms. We're pretty much just going to worry about the protons and neutrons together anytime we talk about the mass of atoms. So next thing, atomic notation. So we have ways of expressing how many protons, neutrons, and electrons are in a particular atom using what we call atomic notation. This is an example. SY is just an example element. There is no element SY, but the atomic number, which we often use as Z, we might say like, Z equals 2, for example. That's the number of protons in the nucleus. So if I said Z equals 2, I must be talking about helium, because I was just telling you how helium has 2 protons in the nucleus and 2 neutrons in the nucleus. So the number of protons in the nucleus is your atomic number. The total number of protons and neutrons together is called the mass number, and we'll use a capital letter A. So for our helium example, where it's 2 protons, 2 neutrons, we would say A equals 4, because it's 2 protons plus 2 neutrons. So we'll use atomic notation to display the number of protons and neutrons in the nucleus of an atom. So the number on top is your mass number, protons and neutrons together, and then the number on the bottom is just the number of protons. Now, one thing that is interesting about elements is that, for example, all carbon atoms have 6 protons. That's a rule that defines a carbon atom as a carbon atom, is all carbons will have 6 protons, and all heliums will have 2 protons, and all hydrogens will have 1. And then elements on the periodic table are sorted by their atomic number. So element 1 is hydrogen, and it's element 1 because it has 1 proton, and its atomic number is 1. And then helium, element number 2, its atomic number is number 2 because it has 2 protons. So you could look at the periodic table and pick out any element and tell me how many protons it has. Aluminum, Al, aluminum is Al, that's element number 13, so it has 13 protons. So then here's just an example. We've got Si, so got 29 and 14. So again, those numbers, the 14, the number on the bottom, number in red, that's our atomic number. That's how many protons we have. And then 29 is its mass number, so protons plus neutrons. So we, going off of the symbol, but also if we're having trouble finding the symbol, we can go off of the number. This element must be silicon. It's actually right next to aluminum. So atomic number 14, that is basically saying that it's telling us that silicon has 14 protons. And then with a mass number of 29, we can figure out how many neutrons it has. So by simple subtraction, if 29 is the protons plus the neutrons, and we know that it has 14 protons, we can subtract to figure out that it has 15 neutrons. So you could take the symbol for any element and figure out how many protons and how many neutrons there are based on the total or any of that information. So just kind of like a summary. So electrons, in terms of the location, they're outside. They're outside the nucleus. The mass, they're very, very small. It's almost negligible. Their charge, they have -1, and symbol is E-. For protons and neutrons, they're inside. So inside the nucleus. For the mass, it's basically about 1, so they have about the same mass, so we're just going to say mass of 1. Now they actually do have a real mass in grams or kilograms, but we're not going to be using kilograms or grams when we're talking about mass of protons. We're just going to be concerned about if it has 4 protons, it has a mass of 4, or if it has 6 protons and 6 neutrons, then we'll say it has a mass of 12. That's going to be good enough when we're talking about mass of atoms. For the charge, protons are +1 and neutrons are neutral, and our symbols lowercase p with a positive sign for protons, and neutrons are 0. Now in this one, maybe you can call this, note some important implications. So electrons, first off with electrons. If you have a different number of electrons than what a neutral atom started with, then we get what's called an ion, where it's got a charge. So charged atom. So for example, helium, my example that I keep on using, helium's got 2 protons and 2 neutrons. And then when it's a neutral atom, it also has 2 electrons that are around the outside. If we had an extra electron for some reason, then now we don't have charge balance anymore. So if my little white circles were my positive protons and the filled in circles were my neutrons, notice I've got, allow me to change colors. I've got a +2 charge in the middle, and on the outside I've got a -3 charge. So the charges are no longer balanced, and we get what's called an ion. So that's how we get ions, or how we get charged atoms, is by removing or taking away electrons. The important thing is we're never taking away protons or neutrons to create charged particles. With protons, if you change the number of protons, you're basically changing the identity. So this has to do with the identity of the atom. All carbon atoms have 6 protons. They could have a different number of neutrons, and if you do have a different number, if you do have a different number of neutrons, then you get what's called an isotope. So for example, we've got, let's see, a 12 right here in this atomic mass. I'll explain in just a minute, but let's say that for carbon, you've got a 6 and a 12. So this 12 is telling you you've got 6 protons and 6 neutrons. You could have a carbon atom with a mass number of 13, so it has 7 neutrons. Or many of you have probably heard of carbon 14. What carbon 14 means is it has 14 total protons and neutrons together, which means it has, instead of 6 neutrons, like this example, it actually has 8. So we can have a different number of neutrons in the nucleus, and it's still a carbon atom. We just now call it an isotope. And how many neutrons that isotope has, you still do a subtraction. So with carbon 14, you would still do 14, where it's protons and neutrons, minus the number of protons, which for carbon it's always 6, and you would get 8 for the number of neutrons. And then if it was a neutral atom, of carbon, that means the number of electrons must equal the number of protons for it to be neutral. And that's kind of like a balancing of charge. So the periodic table is very, very useful in the sense that it can give us the atomic number, the symbol, and the atomic mass for each element. So this atomic mass that we have here, notice one thing is, it's a decimal because it's actually the average weighted atomic mass of all carbon atoms on planet Earth. So most of the atoms on planet Earth have a mass of 12. But as I alluded to, there's some that are carbon 13 and some that are carbon 14. They exist in plants, animals, in the atmosphere, and that's why we have this 0.01. So if you take the weighted average of all carbon atoms across the entire planet, you'll get that the average atomic mass is actually just slightly more than 12. But most of the time it's just 12. And we can get all of this information just from the periodic table.